At the end of lecture A, I mentioned that this integral certainly can be written like this. That's probably the simplest thing to do. But technically, you could also write inverse cosine of x plus c, negative inverse cosine of x plus c, because the derivative of inverse cosine is negative this thing. Let's see why that's true with the picture over here. The graph of inverse sine looks like this. This graph here. The graph of inverse cosine looks like that. Negative inverse cosine would be the reflection of this graph across the horizontal axis. If you're careful, you would see that looks about like this. And lo and behold, if you're careful enough in your drawing, it should look like it's a vertical translation from the graph of inverse sine of x, and it is. They have the same slope separation. That function right there is the opposite of inverse cosine of x. Technically speaking, if you wrote that negative inverse cosine of x plus c, the c would technically be different than this c. But that's not a real big deal. C can be anything, so you can always make adjustments with vertical translations. All right, the main topic of lecture B is twofold: more multivariable calculus, and then something called implicit functions and implicit differentiation. Remind you of this example from last time. Got a mass in a spring with no friction. It's going to oscillate infinitely often if you pull it and let it go, or if you hit it with a hammer, if there truly were no friction. And the period and frequency both depend on two variables, m and k, m being the mass of the object, and k being the spring constant, sort of measuring how stiff the spring is. And there are the partial derivatives. You can check those by hand after class. What I want to show you right at the moment is about these three-dimensional graphs. So we're going to go to Mathematica in a minute here. Before we do, let's just think about these. So m and k are two variables. In a sense, you can let both of them vary over an entire plane here. I want to imagine this plane, that's the bottom of this box, is going into the screen. That's the m and k plane. This is the m-axis here, the k-axis is going into the screen. For each point in that mk plane, you can plot a point whose third coordinate is the period in this case. If you start with an input down here where m is about 2 and k is close to 0, the input would be relatively high. If the mass is 2, say, kilograms, and k is close to 0, newtons per meter is the units, but don't worry about that, the period of the pendulum is going to be fairly high. It's going to be a fairly slow oscillation. The mass is relatively big compared to k. And you can try other points. What I want you to notice here is that, for example, if you keep k fixed and let m increase, meaning you're moving parallel to this axis, k is maybe something non-zero, and you're letting m increase, what's happening to the period? It's a little hard to tell with this picture. If I go into Mathematica, I can rotate it. Go into Mathematica now. Here's the picture. I can rotate this to see it a little bit better. And if I sort of rotate it like this, I'm sort of looking at the graph, the MK axis plane more head-on. I'm seeing essentially these curves being what happens to m or to t for fixed values of k as m increases. M increases to the right. And what I'm seeing is the graph is going up, no matter what k is, no matter what slice of this picture I'm looking at. The period increases with m. As the mass gets bigger, the period goes up. It's a slower oscillation. It should make intuitive sense. And that partial derivative of t with respect to m would measure that slope, that rate of change in this m direction. On the other hand, I could also look at the k direction. Let m be fixed. I could turn the plot this way. Now I want to think of the mass m as being fixed. And let k values move to the right. Now the graph is going down as k increases. The period becomes smaller as the spring constant gets larger. As it gets to be a stiffer spring, bigger, so to speak, the period is smaller, which means it's a faster oscillation. You can do something similar with the period, with the frequency itself. This is the graph of the frequency. As m increases, the frequency goes down. That's a faster oscillation. Slower oscillation. And as k increases, the frequency goes up. You get a faster oscillation with stiffer springs. So you can think about these things in this multivariable kind of way and make these kinds of plots. And you can make it quantitative as well by calculating those partial derivatives, which again, when you do the problems in the book where the function involves more than one variable, so to speak, our book just writes it as ordinary derivatives because it's not, doesn't have any multivariable calculus in it. You can use either notation. You can either write dt dm, for example, that way, or dt dm this way in this kind of situation. It really means the same thing. This is just modified a bit to remind you that the function really depends on more than one variable. There's more than one way to visualize this. Well, let me show you the slices first here. So what I have here with this animation is I'm slicing the graph. Parallel to the m-axis. In other words, k is fixed. But then I can change k. And you can see how it intersects with the graph. And it's always an increasing function. It's just showing you what I was saying verbally a bit more explicitly. And then I can do it in the other direction as well. I can slice it parallel to the k-axis, perpendicular to the m-axis, and let m increase. And look at this, how this graph changes as well. No matter what m is, it's always a decreasing graph. Okay? So a couple other ways to visualize that. Here's a new example. Compound interest. The compound interest formula could be thought of as giving the final amount A as a function of 4 variables. What? A equals f of p comma r comma n comma t. F is the function name. It's not a frequency here. It's the function name. There's the formula. It depends on 4 symbols. You could think of those symbols as all being variables if you wanted to. And you could vary them all at the same time, though it's much simpler to think about if you only vary one at a time and keep the others fixed. But the goal here is just to broaden your mind to new possibilities. And it is a worthwhile thing to do. I could then differentiate these things, this function, with respect to 4 different variables. I could find 4 different partial derivatives. Let's first differentiate with respect to p. Find dA dp. Here, by the way, is an alternative notation you'll sometimes see for partial derivatives. You put the function name and then put a subscript indicating the variable you are differentiating with respect to. That's a new notation. I've never showed it to you before. I don't think I'm going to test you on that notation. I will maybe test you on this notation. It's the same as the ordinary Leibniz notation. But just realize if you do take multivariable calculus, you'll see this kind of notation for this partial derivative as well. If you're physics or engineering, you'll probably take multivariable calculus. If you're chemistry, you might take multivariable calculus. Actually, if you're a business major, if you took business calc, they actually do a little bit of multivariable calculus. explicitly in the business job as well. What would the answer be? Differentiate with respect to p. Treat every other thing as a constant. Treat r and t all as constants. This thing then is just one big constant. This is a linear function of p. In fact, it's a direct proportionality. A constant times p in that case, if you're imagining the other quantities as being constant, which is what you want to do when you take this partial derivative. So the derivative of a constant times the variable is the constant. There it is. That's a constant. When you are thinking of r, n, and t as constants. The graph of a as a function of just p alone would be a straight line through the origin, with a slope equal to this. How about the derivative of a with respect to r? That's a bit trickier. Think. Look at that formula. Treat the p, the n, and the t as constants. R is the variable. That's similar to something like 5 times in parentheses 1 plus x to some power. It's similar to that. It's really a polynomial in R. An unexpanded one. I can use the binomial theorem perhaps to expand it out. I need the chain rule here. I also need the power rule. I need to take the nt power and bring it down in front. Subtract 1 from the exponent. And then multiply times the derivative of the inside with respect to r. The derivative of the inside with respect to r, I hope you see, is 1 over n. That would differentiate to 0. This differentiate with respect to r will give you the constant 1 over n. So that's the extra thing that gets multiplied at the end by the chain rule, and the answer is this. The n's ultimately cancel them. You can simplify for this. Right, I subtracted, I brought the nt down in front. Oh, you know what, I forgot, that was a mistake. There should be an extra p in here. There should be an extra p in there. I lost my p. Here we go. Maybe put the p there. What about the partial with respect to n? Well, I'm skipping that one for the moment. How about the partial with respect to t? With respect to t, this is an exponential function of t, right? Because the t is in the exponent. That's the only place it occurs. The base is not e, unfortunately. So to differentiate this with respect to t, I need a natural log coming into play. The natural log of that base, 1 plus r over n. And then you'll need the chain rule as well because of the n times t in the exponent. There's the answer. The p, I remembered the p that time, times the natural log of that thing, 1 plus r over n, which is just a crazy looking constant, times 1 plus r over n to the nt power. Do not subtract 1 there. This is an exponential function, not a power function of t. Then multiply times the derivative of that inside function there. N times t, its derivative is just n. The derivative with respect to n is the hardest one. The partial with respect to n is the hardest. You got to use a trick to do it. It's called logarithmic differentiation. Well, I'll show you the trick. I got to do it kind of fast because we're running low on time, and we still have more to cover. You might want to rewatch this part of the video. I want to differentiate this with respect to n. Now this is a little funny because n typically would be discrete, 1, 2, 3, 4, 5, 6, etc. And so in differentiating this with respect to n, I'm really treating n as continuous, even though it's not a continuous variable. I could pretend it's continuous if I wanted to. What you have to do is you have to take the natural log of both sides. before differentiating. And you can use properties of logs to rewrite the right-hand side in this way. Now differentiate both sides with respect to t. With respect to n. Take the partial of both sides with respect to n. That's what I mean when I write that. Take the partial derivative of both sides with respect to n. What's the answer? This is tricky. You have to realize a is a function of n here. I could write a of n if I liked. I need the chain rule, really. The derivative of this with respect to n is not 0, because a depends on it. The chain rule says take the derivative of the outside function, the natural log function, which is 1 over x in general, but then plug in the inside function, which is a of n, if you prefer, times the derivative of the inside function, which I'll write as this partial derivative. I've used the chain rule there in a tricky way, keeping in mind that a is not constant, it depends on n. It is a function of n. It's this function of n right there. What about the right-hand side? P is a constant in this calculation. Therefore, natural log of p is a constant. That differentiates to 0. Yay. We like it when things differentiate to 0. Here there are n's. In fact, it's a product of two functions of n. I need the product rule. Left d right plus right d left. Left d right. Oh, I need the chain rule again. What's the derivative of that with respect to n? I can write it that way and use the power rule. This is tricky. I'm not saying this is easy. That'll be negative r to the times n to the negative 2 if I differentiate that with respect to n. I could write that like this. Oh, let's see, this simplifies. I can bring the n squared through the bottom here if I like. I can write on the top, I can write negative n ntr divided by, in the bottom, if I multiply the n squared through, I get n squared plus rn. If I've not made a mistake, that would be the answer. I might have made a mistake, I don't know. But we're not done yet, because we still need to solve for that. I need to multiply both sides by a. The partial of a with respect to n is a times this. Plug in what a equals. Maybe bring the negative sign out in front. A equals this. Wow, what a crazy thing, huh? Make sure you check that after class, because I could have made a mistake. I hope it's right. The overall process is right. I hope I didn't make a mistake. Oh, I'm not. I did make a mistake. I'm not done. I didn't finish the product over here. This was left d right plus right d left with respect to n. So I get that over here as well. And up here, put this in parentheses here. And maybe put the minus sign here. Yikes. This is not on the gateway, you'll be happy to know. I'm not positive it's right, okay? I will check it after class on the video when I watch the video. You won't have a regular homework assignment like that either. But I wanted to show it to you. This, I believe, is our last slide. It is important important with multivariable calculus, for example, to be able to draw what are called level sets or level curves of a function like this of two variables. We'll go back to two variables. That is the set of points x, y in the plane where the function output is a constant. Example, let f of xy be x cubed plus y squared minus x. Task, draw the graph of the equation f of xy equals 1. And find the slope of the tangent lines in this graph at the point 1, 1. Before I do anything, do notice this point does satisfy this equation. If you plug in x equals 1 and y equals 1, you'll get 1 cubed plus 1 squared minus 1. 1 plus 1 minus 1 is 1. It does satisfy this equation. I'd like to find the slope of the graph of that equation at that point, and ultimately the equation of tangent lines of the graph. There's two ways it can be done. One is you can solve for y first, and then differentiate. I should have put and then differentiate. Second, use implicit differentiation. Let's do the second one. That's what's on your assignment. You've got a few problems, maybe 3 or 4. Like this. So this equation looks like this. This is f of xy. The graph of this is some curve in the plane. In fact, I'll show it to you here in a minute. I think all the time. I'd like to find the slope of that graph at that point. What do? You differentiate both sides with respect to x. I'll write a d dx here, and I'll go back to an ordinary d. Because y will be a function of just x, just one variable. So I'll go back to an ordinary d. Differentiate with respect to x. Well, that's easy there. That's just 3x squared. This one, does that differentiate to 0? No, it doesn't. Why? Because y depends on x. Y is a function of x. The graph of this is going to be some curve, and y will be a function of x, it will turn out. In fact, it's two functions of x that you solve for, because you get a plus or minus square root if you solve for y. This y squared really is a y of x squared, if you prefer. I need the chain rule when I differentiate that with respect to x. The outside function is the squaring function. The inside function is y of x. This is not easy conceptually, but I am telling you exactly how to think about it. It just takes some thinking. Read the book as well. Use the chain rule. Take the derivative of the outside function, the squaring function. In other words, bring down the 2 and subtract 1 from the exponent to give you y to the first, or y of x to the first if you prefer, times the derivative of the inside function. The inside function is y of x. You don't know a formula for y of x, that's okay. You can still write its derivative as dy dx. What's the derivative of minus x? It's -1. What's the derivative of 1? It's 0. Now solve this algebra equation for dy dx. Add 1 to both sides and subtract 3x squared. Now divide both sides by y. dy dx at a general point xy is 1 minus 3x squared over y. So at the point 1, 1, if you evaluate this at the point x is 1, y is 1, plug in 1 for both x and y, you'll get 1 minus 3 over 1, -2 is the slope. And that can then help you find the equation of the tangent line from point slope form. The equation of the tangent line would be y minus 1 equals -2x minus 1 because the slope is -2 and the point is 1, 1. That's the same as y equals -2x plus 2 plus 1 is -2x plus 3. Let me end by showing you a graph. Sorry, we're a little over time. We have just found the equation of the tangent line to this curve at this point right there. The one, it's the slope of -2. If I did not make a mistake. The curve is not the graph of a function, it's a graph of two functions. Kind of interesting. See you on Monday.